Okay, so this morning we're going to talk about, during this video, we're going to talk about unsupervised machine learning. That has us over here. You guys have seen this slide before. We've been mostly doing supervised. All right, we did KNN and we did decision trees. But now we're going to move into unsupervised, which, as a reminder, means, we just don't have any labels. All right, no labels on the data. That means we have to identify these patterns without necessarily a target to match them to. Okay, so the one approach that we're going to use in this, and there are many, is clustering, and that's a pretty large space as well. But we're going to do k-means, which is actually something we've seen before. If you remember, we walked through this example, right, where we have a random string of numbers, and the idea is that we need to maximize the distance between these two clusters, right? We're saying we have two clusters, and so we keep trading the numbers back and forth, right, between the clusters until, right, the space between these averages of the clusters doesn't change, and then we stop. Okay, so the starting criteria for this is just a random selection of centroid, all right, and then they allocate out the numbers to those centroids based off distance, and then the machine calculates the average, all right, and then it takes the average of these new clusters, right, the new centroids, based off the allocation, takes the average again, just like it's doing here, right, and then it sees if it's getting better, and it keeps going and going until it doesn't. That's basically it. We're going to get into more details about it. It can be a form of exploratory data analysis. We're going to use it as a model as well, but you can think of it as kind of exploratory. And the way that we think about, the way that we say, move me around here, the way that we reason we say is exploratory, because much of clustering, especially k-means, is done through visualization. All right, so this, you can think of this week as an exercise in data visualization. All right, through the modeling. I'm disappearing here, but you won't be able to really understand the clusters, or at least conceptualize them, right, until you can see them. All right, so much of the analysis is done through the actual development of graphics associated with how the clusters are being represented in real space, right? Okay, so that's why we kind of consider this an endeavor in a data viz, but it's also just a very useful tool for predictive analytics as well. Okay. So there's lots of ways to do exploratory data analysis, okay? I mean, like I said, most of these are done through visualization. This is just a couple of examples here. I actually have a bonus lecture for you guys if you want to work through it in Colab on using text, and we do word clouds and all sorts of things. The sentiment analysis, but basically the idea behind the text mining portion of it is a much broader discussion, but is to take those words and turn them into numbers. All right, that's one way to do it. Network analysis is another. This is where the distance between these nodes is highly meaningful. And then we're do clustering. All these are analytical procedures, but they can be used in a very visual way. So we can think of them as kind of advanced exploratory data analysis techniques, or maybe in kind of the traditional camp of data mining. People might think of it as that. Okay, so again, we got no labels, right? No labels. We don't know what the target is. So that's the key. So we got to figure that out. All right. So what is clustering? Okay, so maybe it's pretty simple, right? So it's a type of unsupervised machine learning. All right. All right. There's many classes of machine learning algorithms, unsupervised machine learning algorithms. All right. We always use a distance metric here. All right. So we're going to have to go back to just like we did with KNN. And KNN is kind of a type of clustering, to be honest. You can think of it that way, is that we're going to have to use a distance metric. We're going to use Euclidean distance, just like we did with KNN. All right, and it's going to be in a hyperdimensional space, but we're going to represent the clusters in 2 dimensions. All right, so I'm going to get more into that. But essentially, the idea is that the closer the data points are to each other in this hyperdimensional space, the more they potentially are related. And that's it. Maybe it's intuitive, but the idea is, can we find these points that are highly related to each other, that are close together, and create boundaries around them and say, hey, anyone inside this boundary, we believe that this type of class, right? This type of variable, right? And then we have to define exactly what that means, okay? This is an example here, all right? It's kind of a classic one, 1997. I realize this is very old at this point, but it was one of the first papers that used clustering to do kind of customer segmentation. All right, so GE Capital, it clustered their customers based on similarity. All right, so it used this to promote credit card bills or to get bills paid better and increase profitability in terms of the way that it was targeting customers. All right. So it was able to bucket these in areas where some were delinquent or people had lots of revolving credit, which is just credit cards. All right. Or this was maybe, and again, without exactly getting through that, these are segments here of customers that were highly valuable in terms of market targeting. Okay. They weren't in delinquency. They didn't necessarily have a lot of revolving credit yet. So maybe they were good in terms of targeting for additional credit cards or other types of financial instruments, right? The important part to remember here is that they didn't necessarily have these labels ahead of time, all right? So they just clustered these groups together and then said, hey, what do these patterns represent? All right, well, majority of the people over here are in delinquency. It seems like that seems to be a pretty clear pattern, and they don't have a lot of revolving credit. And then they were able to use this framework, all right, to develop marketing materials on top of it. But they didn't realize it was going to look like this ahead of time. And that's the idea behind unsupervised machine learning. You don't really know, well, you don't know, right? You don't know what it's going to look like up front. And then when you get it, it requires a bit of a qualitative interpretation. Like, what does this necessarily mean? Like, okay, so we see these groups, great, but what's going on there, all right? And that's where kind of subject matter expertise starts to come in, where you have to dig deeper into what exactly is, what do these clusters mean? How can we look at the different variables that are composing them? And then and start to develop a strategy around them, all right? So in a lot of ways, I think this is fair, unsupervised machine learning is much more complicated than supervised machine learning because it requires kind of multiple steps along the way, right? We do all the same data preparation, we build the models, and in a lot of ways we can validate them the same way by building many at the same time, doing kind of a cross-validation process, and what we did with the trees. But it's not necessarily a canonical output, right? And it could be that even though we're going to look at variance explained, even if it's not a great model, it still might be really, really useful in terms of what it's telling us, in terms of where outliers lie, or how that there's really seems to be really one tight cluster, then maybe totally none other clusters that seem to emerge. But that's information, it's really good. So there's lots of stuff that can be pulled out of clustering, but it does require, a good amount of getting under the hood and taking a look and seeing what's going on. And like I said, interpreting in a kind of a qualitative way as compared to just a pure kind of analytical evaluation approach. It's a little bit more of an art. All right, so we're going to take a look at voting patterns among Congress. This is an easy one because, the voting patterns are highly polarized, and this data is old. Should really have updated it, but it still works. It's still the same deal. I think it's from the early 2010s. But we're going to use k-means. We're going to see, is there a pattern? Is there some structure in this unstructured data? All right, so let's take a look. Okay, so the data set consists of 427 members. It's from, 2013. But trust me, it doesn't really change. And there's three types of votes. We got the yay, the nay, and the other. Okay, so as you can imagine, there's going to be voting heavily on party lines. Okay. All right, so the data points that we're going to have for this example are going to be Democratic bills. All right, they're going to be introduced. So I'll get to that in a minute. So some of the things that we might want to identify with this, say that you're a Republican or a Democrat or a lobbying firm, right? You want to say to yourself, do people historically vote on party lines? I mean, the answer to that is probably yes, all right? But are there some examples of representatives that maybe don't, right? Or is there certain types of bills, right, that may not fall into the same party dynamism, right? So in order to do that, we'd want to create these clusters, right, and take a look and see maybe that there are some outliers. I mean, you can see even here before we get into it, maybe there are, right, if this is a Democratic and this is a Republican cluster. So let's take a look. All right. Before we get into it, I want to talk about the nature of clustering, the idea here, and this is going to be the key point that was going to help you understand how clustering works, okay? There's going to be these measures of the cluster quality. All right, so here we have inter-cluster difference, all right? This is the difference between the clusters, all right, from the very outside of each ring, all right? And then there's inter-cluster difference, and that's the average from the centroid to all the points inside that particular cluster. So this concept's pretty easy, all right? So the idea is that what you want to do is you want to minimize that intra-cluster distance, all right? Easy for me to say. You want to make that as small as possible, but the space between the clusters, right? You're going to make that as large as possible, but they play off each other, right? If one's tighter, the other one's going to be bigger, all right? So there's an effect. There's a push and pull there, all right? But that's the idea. Like if we had perfect clustering, you can imagine, you'd have like one really tight cluster down here, another one like way over here, right? Like, oh my gosh, right? These two groups are totally different from each other. They're tight and they're super far apart, right? So that's intuitive, right? But how we measure it is a little less intuitive, but we're going to walk through it. All right, so the centroid, and again, we talked about this before, but the centroid, as a reminder, is the average, all right, distance from all the points to that centroid, okay? All right, so it's the average, it's the middle of all these points that have been assigned to that particular cluster, right? There could be 8 of these, right? And so all the points that are assigned to that cluster, it would be the average distance using Euclidean distance to that centroid, all right? And, so you can think of it another way. The centroid minimizes the distance between all the points in that particular cluster, all right? It's the middle point. It's not necessarily a point itself, all right? Could be, but it's just a middle point in that particular clusters. Okay. So 4 steps. In K-means, we've gone over this, but we'll do it again. All right, so say this is our data, right? These are the number of nay votes here, and these are the number of yay votes here, right? So we assume this would be Democrats and this would be Republicans. If these are, Democratic introduced bills, so Democrats are going to vote for it and Republicans are going to vote against it, okay? So the first thing we do is we just randomly select 2 points, right? Okay, just randomly select, just like we did in our example that we walked through. Those are just thrown on there. They could be anywhere, okay? And that's an important thing to remember, right? That's why we need to set our seed for this in particular when we go to do it, because these points reset every time, all right? And then what happens is that the points get allocated to each cluster, all right? So this isn't a perfect example, right, in terms of where these clusters are sitting. So just, work with me through this kind of theoretically. But the idea here is now that, these random points, random centroids have been put on. All of these points are assigned to the centroid that is closest, right? So each point gets assigned to whichever centroid they are closest to. And that's just Euclidean distance, all right? All right, so this point will go here, right? This point will go here. You guys get it, okay? So in theory, this is what it would look like afterwards, all right? And then what would happen, right, is that those centroids would be recalculated based off the new cluster membership, okay? So as our centroids, remember, they were like over here and over here before, but now once we allocate all these points, it just takes the average, right? So it tries to find the middle point of all of these clusters, right? Finds the middle point, and then it just recalculates the centroids, all right? And that's it. And so this process just keeps going, and then again, based off this new, right? Based off this new reallocation. And as you can imagine, the most gains are going to happen, right, early on, right, in this process, right? After that, it's going to be kind of small movements of the centroids inside the established clusters. Unless you have many clusters, then they can move around a lot. But if you have, less than 5, something like that, it's not going to be a whole bunch of change, in terms of the number of steps that it takes for this to fit. All right. So right, and so it just keeps going through this process again and again until no additional change can occur, until the space between those means has been maximized. Just like we saw in the numerical example where we worked through it, right? There made no sense to reallocate, right, the numbers in between the groups anymore because they were as far apart as they could get. Any reallocation would actually result in depreciation of the model, right? It would make the model worse. So that's how it stops, right? So when it knows that it's maximized that inner and intra, all right, cluster difference, okay? So that's all this says. It just repeats those steps over and over again. As we can see here, right, what's going on, this might be really useful, right? Is that, in this example, there appears to be, right, some people that are classified in cluster 1 that seems to be much more dominated by Democratic votes. It looks like I think I may have misspoke earlier. I have two data sets. I have one for Republicans that are introduced the bills and one that for Democrats. It looks like this is the Republican one, because this is the number of yay votes here. And as you can imagine, Republicans will vote for Republican bills, all right? And Democrats will vote against them, all right? So these are likely Republican introduced bills. But it seems here that there are a few, I'm sorry that there's some noise in the background. It seems like there's a few Democrats, right? Or I'm sorry, Republicans that are voting kind of more in line with Democratic patterns. Generally, they're not, really far up into the cluster. Maybe like this person is here, right? Right, but they are simply not in the center here. So we can think of this center point as kind of, that is voting exclusively on party lines. So there's some variation in terms of the patterns with which they are voting. Okay, so that might be useful for us to explore and get a better understanding of, like, who are these particular representatives, right? And they might be the ones that, if we were introducing a bill, say we're a Democrat, we were introducing a bill, they may represent swing votes, right? Because it appears that, at least in comparison to their peers and in comparison to this, kind of the tightness associated with this cluster, is that they do have a tendency, whoever they are, to vote kind of along, not necessarily along party lines. And that's good information for us to have. We also notice generally, I think it's fair, if you look at the patterns associated with Democrats or Republicans, is that the diffusion of the Democratic voting pattern is I don't say much, but it's certainly wider, right, than the Republican. Okay, so we can see here that just in generalities, right, this is a much tighter cluster. And we could actually measure these individual clusters, and we'll see this as comparison to the Democratic one, right? And that's good news for Republicans, all right? So Republicans are kind of staying on party lines, depending on your view, of course, of political dynamism, are staying on party lines, but that Democrats not as much, right? So they may be more subject to, vote in favor of some of these Republican bills. So that's interesting inside itself. There's a lot of code in here. I'm not going to spend a ton of time on that because we're going to go through it in class. It's all in the slide, so if you want to start working through it, and then I uploaded our script up to the Colab, so you can take a look at all of that. Okay, so I'm just going to keep going. All right, so here's an important slide. All right, so these are all the measures, essentially, of the variance or of the patterns associated with the clusters themselves. All right, so the total sum of squares, right? This is the sum of squares, the distance between all the points, right? And this is measured from the global mean of, oh God, I'm gonna have to write out global. This is just a mistake. It's from the global mean of the entire spread of the data. So we're going to normalize the data, right? And then we're going to project it onto a hyperdimensional space. And you can think of this as the core, right? So it's the core of the Earth, assuming there's a perfect sphere, whatever. It is the middle point of the entire spread of the data, right? So we measure every point, every distance, Euclidean distance, every point from this global center. And that total, right, that total spread is what we call the total sum of squares, okay? Distance from all the points. All right, the between is just a thing that we saw before. I just highlight these two because it's easier to talk through two of them, because the rest of them are basically just derivations of these two. All right, so between the clusters is the distance, right, between those boundaries of the clusters, right? And that's a calculation. You can think of the total sum of squares error minus the total within sum of squares error. It's easy for me to say, right? But the total within cluster sum of distances is the distance from every point, right, to the centroid that is assigned to that particular cluster, and then it's summed up, right? So you have two of those, right? So you have one for cluster 2 and one for cluster 1. In the example we saw up here, right, the total variance in this would probably be larger, right, than the total variance here, okay? So what happened is that because of that, right, the between distance between these clusters would be smaller, right? So more variance accounted for in terms of the cluster, not necessarily great, right? We want that to be tighter, all right? We want those clusters to be tight. We want the space between them to be wide. All right, so when we do this ratio, essentially, all right, which is just the total sum of squares minus the total within this, right, which is just a variance accounted for by each of the particular clusters, we get this between measure, all right? And we'll talk a little bit more, but in just a second. So here, this is better. I can show a little visual example. All right, so, and then another way to look at total sum of squares error, right, is just it's going to be the inter-cluster difference, which is the between sum of squares error, and the within sum of squares error. You add those two things together, it should be the total sum of squares error. Okay, that's all the error on the plot. Again, there's a bunch of code here. Okay, and the quality of this graphic is terrible, but this is for democratic induced bills right here. All right, so we can think about the two clusters here. I think this label might be wrong. All right, so again, these are I'm just projecting the perimeter essentially of these two clusters just to show you it with real data. All right, so here we can see it's clear that two groups exist. All right, group 1 and group 2. Right, and then how do we infer the differences between those? Well, we use those calculations that we just went through. All right. Okay. So I think this pattern is a little bit more accurate here in terms of the way that we're projecting it with the Democrats down here and the Republicans up here. Okay. All right. So just showing that same thing again. And then here again, what we have is kind of outliers. These could be gauged as, and then maybe some over here too, right? Be gauged as targets for potential lobbying activity, right? Or you're going to reach out to those and say, hey, it looks like you're not voting traditionally along these party lines. You maybe want to go into a little bit more history about what are they voting for and what they aren't, and see if they can bring them over to your side when you introduce a new bill. It would certainly be interesting to see how this occurs over time, to see if polarization is increasing. My suspicion is that it is. All right. We could also look at it this way. I'm going to show you guys in code how to do this. All right. Kind of do a 3-dimensional plot. All right. Where you can flip it around. And here we have all 3 pieces of data aside from just nay and yay. We also have the other votes, which ends up being a pretty small percentage. Others are just like abstained or not present and absence, something like that, which is the biggest. They're pretty minority in this particular group. But this is a nice way to look at it, and I'll show you guys how to do some of these 3D graphing so you can kind of flip things around. And that allows you to see more of the influences on the data points as compared to just 2. Okay, so again here what we're trying to do, how good is the clustering? We're trying to maximize the separation and keep those clusters together, all right? So one of the ways that we're going to look at this, right, is we're going to explore a variable called variation explained. All right, so the total variation explained, it's just going to be the inner cluster variance, which is the between sum of squares divided by the total variance. All right, which is just the total sum of squares. Okay, so we're just going to divide that. What is the ratio of all the possible variance? How much of it is in this between space? All right, so that what leaves us with, right, is basically how much of the variance is explained by the clusters. Right? So it just says, given the differences between them, given the space, which is good, we want as much space, how much is left over just in the clusters themselves. And that'll tell us the total variance explained by the particular clusters. All right, and we can use this calculation. It's the same slide again here. We can use this calculation. Let's show you down here, right? In order to optimize our clustering algorithms, right? We can use it just in the elbow method, right? We can select a bunch of different numbers of clusters, right? For here, we kind of knew that there was going to be 2 because of Republicans and Democrats, so we had kind of a lead in there, which makes it easy to show. But it might be that we don't know that, right? In most cases, you don't, all right? So we can use this measure, and we want to optimize this, right? We want our clusters to explain, given what's left in terms of the total variance, how much is explained by the clusters themselves. So that's what we want to try and figure out. And so we can do that. It's pretty easy. When we do a k-means, we'll have all of these measures, and we can just create this little calculation. Basically, just divide, the total sum of squares error here, right, denominator, right, by the between variance, and we just get a ratio. All right, higher the better. All right. So that's how we can optimize, okay? There's other ways to do it too. But this is an example. You guys can remember this. We use this elbow method just like we did for KNN. NBClust is basically a package inside R that we'll talk through, which runs a whole bunch of different models and then uses majority vote. As you can imagine, there's many ways to do clustering. Basically, the variance between the methods is dictated by the measure that they use. All right, it's just how they measure distance. That's pretty much it. There's other things to get into there, but if you think of it just that way, there's lots of ways to measure the distance between points. And so many of these clustering methods use different approaches to measure it. Euclidean is the almost kind of universal approach, but lots of other ways to do it. All right, I'm just going to walk through these real quick. I'm just going to walk through these slides real quick and try and get to the point where we see kind of this graphical output. All right, we're going to go through all this, and here we go. So it'll look just like this, and here we see kind of our, this is our optimization function here. You can think of it that way. We're trying to optimize this variance explained. And then we just see this elbow method, right? Just like I said before, typically much of the benefits of this clustering approach are going to be realized really early on, and then after here, this is all this is in diminishing returns, right? So maybe we could go up to 3. That might be interesting, right? Like we showed. Sorry, not to make you seasick here, but we showed here, all right? And maybe 3 is better in terms of the way that we're thinking about this data. Maybe 3 represents a segment of representatives that are simply not voting very tightly along party lines, right? So even if the variance explained just goes up a little, it went up a non-trivial amount, maybe 8%, maybe 3 is the better approach just because it's easier to visualize it, right? So tagging these people as 3s makes it easier, all right? We still have this guy over here, right? Extreme outlier, but maybe that's a better approach just because it's easier to visualize what the goals are for this particular project that we're trying to capture, right? Beyond that, I can't see any advantages, which is the nice part about this elbow method. It makes it really simple. NBClust will do things by majority vote. We'll get into more of that. See if I get down to where we have the graph. Yeah. Essentially, these are all the number of clusters, the number of clusters recommended by each of the methods, okay? And then the number of votes, the number of methods that voted for that number of clusters, right? So here we have for the number 2, right? We have, over 12, more than half, assuming there's 30 of the methods essentially voted that 2 was the best number of clusters to optimize the algorithm. So this is how this works. It just tries a whole bunch of different methods and then sums up which ones voted for which number of clusters. And then you can see it kind of nationally. Where with 12, that looks like it's more. You can see it right here graphically. Okay? All right. So I'm running along here, so I'm going to start wrapping up. All right? Certainly, we could see pattern differences in Republican-led bills as compared to Democratic, all right? It could provide information on congressmen for swing votes, right? So there are some limitations that we need to be aware of, assuming the patterns correspond with bills being voted, or perhaps congressmen have the same number of yay or nay votes, but they voted on different bills, so we wouldn't get that, we wouldn't get that nuance, right? Exactly about how the patterns are associated with particular bills. So it's really kind of an aggregate measure, all right? Network analysis might actually be better, right, in terms of to think about the relationships between particular congressmen. Maybe it's that there's some geographical kind of voting patterns that need to be sparsed out, and we don't necessarily have that here. All right, and so we can't take into consideration all these, extenuating circumstances, right, in terms of political initiatives, things like that. It's very high. That's why we think of it as kind of an exploratory measure, but in many cases it works really well, right? Okay. So the good is that it's cheap. There's no labels. Labels are expensive and take a heck of a lot of time. All right? And think of armies of interns labeling dogs versus hot dogs, right? All right? I know this is going to sound counterintuitive, but clustering always works, right? If you have no clusters, what it tells you is that you have no clusters, all right? And that's information that you can use, all right? It might be that you need to go back and rethink about the questions you're asking of your customers or the data you're gathering, right? If it's not providing you information, then that's information in itself. So it always works. And typically there are at least 1 or 2 clusters that work really well, and then there could be some diffusion amongst the others, all right? There are a ton of different ways to do clustering. I mean, just I mean, here, just in NB class, we have 30 different methods, and that's just for k-means. There are a lot, right? They fall into kind of, broad categories. You can think of them as kind of unsupervised and hierarchical. Right? We're not going to talk about hierarchical, but anyway, that there are many methods. That's the point, and sometimes it's hard to choose the right one. All right, we have a dimensionality problem. If a space starts to get too complex, main clusters are probably just not going to work. You have to go to some type of network or more sophisticated model. And just like any other bad data in, bad model out. All right, k-means does not get much better with large amounts of data. You can kind of segment off, and then if it doesn't look like there's some type of patterns emerge, sticking more and more information in there usually doesn't make it significantly better as compared to other machine learning methods that it might. Okay. It can handle spherical data. I'll explain that in a second. And unequal cluster sizes may do weird things to k-means. All right, so let's just take a look at this real quick. I think this is the last slide here. I'm running a little long. This is an example of spherical data. You see, it's in these circle patterns. All right, and this isn't all that uncommon. Okay, and so what k-means does, right? This is a centroid, and this is a centroid. So what it does is it divides this data in half instead of clustering it in the proper pattern like we see here, okay, which dbScan, which is just another approach, can do. All right, so there's another example of it here where we see that just the nature of the algorithm in terms of how it is optimized doesn't handle well with these types of waveforms. All right, so here it has the dividing line again, kind of in this horizontal pattern, and really what it should be doing is identifying these circular patterns, which is properly identified here. Okay, the same is here. If you have two clusters that are really closely related to each other, it may sub-optimize it, right? Say, hey, these are the same thing, when really it appears that they are different. So that happens. Okay, and you can see here spectral clustering does a pretty good job, but it might not do a too good job with this, right? This is just an example of many different models being used on the same data. All right, mean shift has the same problem here. Anyway, I'll let you continue to explore, and Ward is just awful across the board. Okay, so with that, all right, k-means is computationally pretty cheap in terms of just putting things together, so that's good. These other methods, maybe not so much. All right, so there's some advantages there. All right, we'll go through some of these when we get into class, and I'll see you Thursday. We'll walk through all the code. All right, thanks a bunch.